So, I think right now, though, I would like to get started with some things. So, first things first, we have exam 2 in 1 week. And I know, we're reeling from other exams and other things going on in our lives right now, but it's just that season, unfortunately. It is going to be covering all of our stuff as we had seen it from, since exam 1, all of our material since then. So that is 7, 8, 9, and 10 will all be on this thing. Again, roughly even distribution between all of these things. Of course, there's going to be a little bit of chapter 6 kind of pulled in there as well by the nature of what we've been doing. Right? I might even have some questions just specific to chapter 6 on that just because it's important stuff. Right? We're kind of doubling over on forces. We talked about forces on exam 1, but we have continued using forces for, well, even in energy, we're still using forces. So I think those are pretty important to talk about. Yeah, same format as before, same deal as before. I'm going to have some practice questions after the lecture comes up today. I'm going to have some of those extra credit questions as well, just some small things that I have repurposed so you can be familiar with the format, get a little bit of extra credit on your mastering grade if you'd like that. Yeah, all that good stuff. The due dates are also going to be just a little bit wonky for some of these things. You might notice, like some of the questions for this one, I have moved some things around to be a day later or something else, just because tomorrow is supposed to be our second day of spring break. And I realized the dichotomy of saying that there's an exam coming up in a week and then also trying to encourage you to take a little bit of relaxation on Tuesday. Whether or not you choose to, please, at the very least, get a little bit of relaxation. If you're going to keep working through spring break, if you want to use that to catch up or get ahead on some different things as you choose to do, I'm, of course, not going to tell you how to run your life, but I am going to ask, please do consider getting a little bit of a break. I think everyone getting just a little bit of a break is always a good thing as we can. Homework still due today. Yes, because that is homework from Friday's class, but the homework from today's material is getting pushed back by a day. Exam 2 will cover some of the same things as exam 1 purely by the nature of physics, right? If I'm asking you, I'm not going to lean super heavily into that. Right? We're not going to see a pure projectile motion problem, but you might be asked to find stuff like a final velocity or something else that could be done with kinematics. Now that we've got some language about energy, we've got a lot of flexibility on how we can solve a lot of those problems, but generally speaking, because we keep building on top of older material, there will be some material pulled from stuff like that. It's mostly going to focus 7 through 10, maybe 1 or 2 questions on just chapter 6 because forces are big important. And the exam is the 15th, correct? Is there a quiz to go with today? Yes. So, let's go ahead and talk about sprongs. Which is not just a joke that I'm making up. I'm pulling it from the book. I promise I'm not just a crazy person. But let's go ahead and dive into some of this stuff. So, quick recap on some of the details for this one. When is third exam? I am going to be updating the calendar on that one very soon here. I didn't put out everything at first because I wasn't entirely sure if we'd have any sort of disruptions or anything, and I didn't want to redo a whole bunch of work. But now that I'm fairly confident we're all on track with everything, exam number 3 is, my agenda's behind me somewhere. I think another 3 or 4 weeks from exam 2. It'll be on a Monday as well. I remember that. So I think it's exactly 4 weeks away from exam 2. But anyways, what we have been seeing from last time, all of this good stuff, right? Here's kind of the sum up, our handful of really big equations here. I think the only one missing is our equation for kinetic energy, right? That 1/2 mv squared, but we have seen that a couple times now. We had this idea that if work is being done on an object, then that work shows up as kinetic energy, right? Or rather, a change of kinetic energy. An object that is moving that has more work being done, and it might be slowing up or speeding down, or said that the other way around, slowing down or speeding up. An object that is not moving, that has work being done on it, is probably almost certainly going to start moving. The sign of the work depends on whether or not we are contributing to or taking away from that kinetic energy. Sometimes, if you have a very fancy work being done, specifically what we call a conservative work or from a conservative force, then you get what we call potential energy, right? And it's kind of the difference between friction and gravity, right? Because in gravity, we know it's going to be there. If we lift an object up now and we let it sit there for a little while, we know that when we let it go, gravity is going to be there to release that energy back, right? Whatever work gravity did before when we put it up there in the first place, it's willing to let go of that again and put that back into kinetic energy. Friction is not so kind. Drag is not so kind, right? Those dissipative forces are essentially just going to be taking away from energy whenever we would want it to be there, right? It's not going to give the energy back, and that's one of the really big differences here, right? If I lift something up and then drop it back down, I gave gravity a bunch of energy, and gravity gave it back to kinetic energy. But if I do that with friction, if I slide a block across the slope with friction, friction takes that energy, dissipates it into heat and sound and other things, and we can't get that energy back. We can't pull that back into kinetic energy. Not easily, at least. That's something for next semester. So for the most part, that's our big difference between a conservative force and a non-conservative force. A conservative force we can depend on. It's going to be there in the exact same quantity, pulling the exact same way, completely independent of path every single time. Whereas non-conservative forces, friction being our biggest one, don't do that. Because gravity is so important, we even give it a special equation. Gravitational potential energy is always just mg, the force of gravity, times the distance it falls, y. Then we had this big idea that you conserve mechanical energy, right? Any energy that I start with should be the exact same energy that I end with, so long as we don't have anything messing us up like friction, right? But if friction is involved, we have ways to deal with that, and we'll talk about that in just a little bit here. So first of all, let's dive into a concept check here. Let's imagine a particle with potential energy shown in the chart is moving to the right. It has 1 joule of kinetic energy at x is equal to 1 meter. In the region x, between 1 and 2 meters, so specifically this portion of the graph, everything froze. Oh no, okay, we're back. Sorry, my computer saw a pen and freaked out real bad. So this region right here that we're looking at, what's going on with the particle? Speeding up, slowing down, moving at a constant speed? Do you have any idea? Any of that good stuff? One answer, two answer. What else are we thinking here? We can assume there's no friction or anything else like that. Okay. Couple answers here. We have managed to form some sort of pop icon out of our answers in chat. Thank you. So, but I think we're all split between speeding up or slowing down. Right? We're somewhere between those two. Speeding up or slowing down, we're like, okay, no constant speeds here, right? We see a change of energy. We're certainly changing energy. But we're talking about a potential energy being shown in this graph. What if we had changed this instead to gravitational potential energy? Let me change this to gravitational potential energy. So U of G is equal to mgy. So then really what I'm doing here, because mg is not going anywhere, right? mg is a constant the entire time. Then what I'm really looking at is a change in y. I can visualize this as if it is a physical hill. Right? Imagine it's actually like a physical hill that is shaped like this. It's a little bit jagged. Maybe we'll round it out a little bit more. But for the most part, I can imagine this thing just like a hill. So I've got, a small peak to that hill, then I've got a little bit of a valley going into this one, and then we rise up the main slope of the hill. If I see the ball, or whatever I have, the particle, I guess, moving, it has a kinetic energy when we're at the peak here, then I can imagine as it continues to roll down the hill, it's going to speed up. What we're saying here is that energy must be conserved. Whatever energy we started with, so we started with some potential energy and we started with some kinetic energy. By the time we get all the way down to the bottom here, we have run out of potential energy. Everything we have is now going to be in kinetic. And because everything we have is going to be in kinetic now, we have to know that we're going to have sped up through that process. How do we feel about that description? Are we all a little bit less ABBA, a little bit more ah? It is indeed A. It should be speeding up. Yes, since all energy is conserved, exactly. We had potential in kinetic. We end with only kinetic. That tells me that my speed had to have gone up. All of that energy that we had in potential is now being converted into kinetic. Okay, I'm going to try another one here. Or maybe not a concept check, but something a little bit spicier. What about something like this? This is a really good one. This has got a lot of pieces to it, right? We get to tie in all sorts of things into one problem together here. So let's imagine a roller coaster car on a frictionless track. Easier to deal with already. Shown below starts from rest at height h. Right? So this is a classic roller coaster. They bring you up to the top of the hill, and then gravity takes over and pulls you down the rest of the way. The track's first drop and following hill consist of circular-shaped segments of radius capital R. So first, what is the maximum height in terms of R from which the car can start and not fly off the track when going over the hill? Second, for the height found, what is the apparent weight felt by the riders at the bottom of the valley? So first, we have to find part A. Part B is talking about a normal force. Remember that. That's the normal force, apparent weight, normal force. But part A here. Let's talk about what we can do with this thing. Maximum height in terms of R that the car cannot fly off. Think about what that means. Think about what it means to stay in the circle. Think about what it means to fly off. Think about what, if we're going a little bit slower than that, what forces do we feel at this point in the track? And which of those things can go to zero and we be all right? One of the forces acting on us at the very top here is going to go to zero. And when you're doing that, we still maintain our circular motion at that point. I'm going to say take the next 4 or 5 minutes, then we're going to talk about part A. Then we're going to pull that back and dive into part B. All right, so let's start talking about what we've got here. And let's work from that. So first things first, we need, of course, a fantastic picture. I'm going to try and draw some of these circles here, and these are going to be real bad, and apologies for that. We're like right here. That could be worse. We've got a track that comes into this circle, something like this. We've got the actual track going something like this, roughly. Oh, yeah. Look at that. Amazing drawing skills. Piecing it together once again. So we know in both of these cases what we've got is something radius r, radius r. Let's pretend that those radii are all equal. And we know that we start, did I go to art school? Oh yeah, you know it. I was in that School of Creative Arts for too many years. We've got a car when we start, and let's go ahead and label this right here h. So the big part that we need to look at first, right? We don't really care about this dip that we have in the middle of this thing here. We need to talk about this spot right here. I want to make sure that I actually have my picture. Oh, it's from the middle of the circle. Oh, that was not drawn to scale at all, was it? Yikes. Yikes. Well, that wasn't great. Oh, I can't. I have so much trouble copying these pictures. It's probably going to try and copy the vector. I think it always tries to do that. Can I have it pasted as not a vector? Can we, no, it wants to do as a vector. Somewhere here. I thought I had something for the log that I could do this with, but perhaps not. Okay, we want to draw this thing accurately. So give me a second here. We want to make sure we're actually drawing this thing accurately, because how this picture lays out is pretty important to do. So we got from where h is going to be, so this is level with it, and then we got the rest of this thing is going to be something like this. That's a little there. I'm trying, well, I could try to take an actual screenshot if I would a real screen right here. But not this thing. Let's try that. Let's try an actual screenshot of this thing, see if that works right there. It's just such a nightmare. It used to work totally fine. I don't want to sketch. We're just going to snag this bad boy, see if that works for us. Ah, there we go. It used to work totally fine, and then they had nothing to create, and everything was ruined. Oh, jeez. Where's all mapping layers? We're going to get rid of this. Okay, we're getting there. It wouldn't be a 191 lecture without some sort of technology disaster. Can we move there? Okay, it's being a little bit clunky, but there we are. Can even try to make this just a little bit bigger so we can get a good view of what's going on. Perfect. So, good idea on that one. So this is probably a little bit easier to look at than what we were looking at before. But we really don't care about what goes on in the middle here, right? That's a pretty big deal. I really am not concerned about anything that goes on this side of things because that's not where I'm looking. Whatever happens down there, I'm not going to fly off the track in the bottom of the dip, right? I might have enough G-forces that some people might pass out, but that's a different story, right? We care if they fly off the track because that's when actual safety and structural damage comes into play. So let's think about what happens there. When the car is at this point, point 2, what type of energy do we have? Some potential, but also certainly some kinetic. But I would argue that at a certain point, the kinetic is probably the least important. Let's talk about it like this. When we start, we know we have nothing but potential. Call it MGY0. That's when we start. Now, what if we didn't plan this out very well? What if we made a really bad ride and it just stops at the top of that loop? It gets up to the very top right here, and then it stops. That's all right, but at a bare minimum, it has potential energy. So we know there has to be some potential energy equal to at least mg capital R, but I'm also going to assume that while we're up here, you know, they have already kind of stated we've got some velocity. If I'm making a roller coaster, I have to assume that they go through the rest of that. So I'm going to also assume that there is some 1/2 mv2 squared velocity associated with that spot. So right here, this is all I've got. We don't know what y0 is. We're not entirely sure what this height is actually supposed to be, right? That's the entire point here. We're looking for this. What is this? What does that have to be, or what's the biggest that could be before we fly off the track? So if I want to know what y0 is supposed to be, I already know r, g, that's just a thing that shows up, and we can kind of see, we can immediately cross out all of our m's. We don't need these. We don't need any of those. They all cancel out. But the thing that I do need to focus on then is I need to figure out what can v2 be. What v2 is going to tell me what my initial height needs to be. So let's go with that approach. Then we can say, okay, well, what's going on with the car at that point? Let's draw that part out. Let's just focus on that single part. We say, all right, we're on top of a circle, something that looks kind of like a curve like that. We've got our car, you know, it's got some velocity associated with it, v2. And I'm even going to make that a dotted line to say, hey, don't you forget, not a force. What forces do we have acting on us at this point in time? Gravity, certainly. And also normal force. Yeah. So let's think about it like this. Let's say we say, safety, not as important as the thrill. What if we let the car launch off? What would change about our free body diagram? How do we know when we launch off? How do we know when we actually, go airborne? What does that mean to go airborne? No normal force, exactly. There can't be a normal force where there's not contact anymore. If we are to go airborne, then we will have eliminated our normal force. Gravity is still going to be there. Of course, gravity is going to be there. But then we can kind of assume, okay, well, let's not go to that extreme of launching off. Let's go to a little bit less of an extreme. Let's go, we get over it, but we're still moving. Can we agree? The faster and faster we move, the closer and closer we get to going airborne without actually getting there. And that means that every single time we speed up just a little bit more, this normal force keeps getting smaller. So we say max speed without launching. Without launching, right? Because again, and am I spelling launch correct? Yeah. When our normal force trends to 0. When the normal force is not doing anything for us anymore, that's essentially as close as we can get without truly getting airborne. That's the tracks are like lifting up by a millimeter off the track before actually coming back down. Right? That's when we're in lawsuit territory, but perhaps not quite yet. So then, let's think about what that means. Well, if the normal force is going to 0, but we are still constrained to moving in a circle, that means gravity is the one that's actually responsible for keeping us in the circle. We know there has to be a centripetal force. We are moving along a circular path, so our net force must be equal to mv squared over r. So let's do that. Let's say our net force in, we can call this direction positive y if we would like, or better yet, let me use my notation here. Let's call this the r hat direction, right? Going towards the center of the circle. mv squared over r is supposed to be our net force. It's mostly coming from gravity, but normal force would be taken away from this as much as it needs to, right? And this is, think about what happens whenever you drive over a hill or anything else like that. And if you're driving into Oxford at any point, you probably know what I'm talking about here. You go over one of those hills, you feel like a little bit of a lurch up in your stomach. That's what's going on right here, right? Your normal force decreases while you're going over that curve, and then you sink back down into it. So we're looking at the circumstance where we have maximized this. We've pushed it to an extreme because safety be damned. The normal force goes to 0. Gravity is the only thing providing our centripetal force. This is the maximum speed. If we go any faster than this, gravity can't increase to compensate for a faster speed. If we go any faster than this, gravity is not enough to keep that centripetal force. We're not in a circle anymore. We're going airborne. Does that all make sense so far? So when we do this, what we find is that our maximum speed is equal to the square root of that radius, and this should be a capital R, I guess, shouldn't it? Our same old capital R times g, square root of that full thing. That's our maximum speed before we fly off the top of the hill. If that's our maximum speed before we fly off the top of the hill, we come back up to here, to our energy. We now know V2. So what does this thing become? This becomes G times Y naught is equal to G times R plus 1/2 V squared is going to be just RG. That is to say, cancel out all the G's. We don't need all those. Gone, gone, gone. Our initial height must be 3/2 capital R. That's the maximum height before, that thrill becomes a little bit too much. So minimum height, 1/2 R, or just R, I guess, right? We need enough height to actually get over this thing, but we don't need so much height that we're going to fly off on the other side. Somewhere in between those two is perfect. And realize this is like a big part of, you know, there's a lot of safety things that play into this and everything else. Whenever you're talking about how do I reduce a speed without introducing a lot of friction or anything else like that, right? Roller coasters are a perfect example of this, but cars and everything else are just as well. It's part of the reason why you can't have traffic lights too close to bridges, right? Which is a little bit of a strange rule sometimes, but you know how a lot of bridges, or especially overpasses, will, you know, kind of rise up a little bit, right? That is potential energy that the cars are going to have to convert their kinetic energy into potential energy. You can't have a traffic light too close to those things, because if you do, then older cars that don't quite have that engine power are just going to be stuck. They can't create enough energy to actually get up the hill. You need already to have that kinetic energy to transform it into the potential. My mv squared over r, remember, that is my centripetal force equation right there. That is equal to any time we are moving in a circle. If we are to continue moving in a circle, that is my net force in the radial direction to make sure that I stay in the circle. If I don't have that, then I'm not moving in a circle anymore. So let's take this. Let's go back to part B here. Let's look at the circumstance. Okay, well now let's imagine we're at the bottom. What is my normal force down here at the bottom? Knowing all of that information so far, what is my normal force at the very bottom dip? Take the next 3 or so minutes and come up with that one. We've got a lot of the similar steps from before. So let me go back to my picture on this one. We're looking for the normal force felt at the bottom of the ramp. Give it the next 3 or so minutes, then we'll come back and look at this thing together. All right, so let's start diving into this thing. Again, we're kind of enhancing some of these steps that we've got so far. So now we know what our initial height was supposed to be. We know what the initial height is supposed to be. We need to take all of that into account when we're looking here at what's going on with the bottom. So here's what I'm thinking. At the very bottom, our free body diagram is a little bit different. So let's highlight that. At the bottom curve, man, one day my handwriting will look a little bit better on digital draw pads, but today is not that day. If you want a rough comparison, the Exam 1 solutions are up and posted now, if anybody hasn't seen those yet, where my actual handwriting shows up a little bit better on that one. Got a lot more pride in my physical handwriting than I do my digital. So what we've got here, we still have a normal force pointing up. That is no different. We still have a gravitational force pulling us down. That is no different. The magnitudes of these are what might be changing a little bit more, right? Because now our centripetal force is going in the opposite direction. We're in a circle that is essentially, our centripetal force needs to point upwards now, right? So what's doing that is now going to be the normal force. We're now not having the normal force and the gravitational force essentially, well, the roles have flipped. Gravity was supplying our centripetal force this last time. Normal force was counting against that. Now normal force has provided the centripetal force. Gravity's pointing against that. So then, what does our equation look like? Well, we still have that our net force must be mv squared over r. We're definitely moving in a circle. And I guess I should do capital R for that one. We have the normal force pointing in the direction that we want it to be. We have gravity pointing against that. And gravity we can't get rid of, right? That's never just going to go to zero. The normal force here is going to be whatever it needs to be to make sure we stay in the circle. So there's no direct quantity that we plug in this normal force, but instead we need to look, okay, we're after the normal force. What do we need before we can find that? We know capital R. We're going to cancel out m's. Just don't worry about that quite yet. What we need to find first is what is v. So what is v? Where do we get that from? How do we know what the velocity at the bottom of this thing is supposed to be? Go back to our picture. what has happened to all of our energy? From the beginning to point 1, what has happened to all of our energy? How has it transformed? It started from potential energy. It has all gone to kinetic energy. That is exactly correct. It is not split between the two in this case. In part 2, right on top of the second hill over, some of it was potential, some of it was kinetic. Here down at the bottom, this is our greatest speed rush because all of the potential energy has been converted to kinetic. We're down to level ground. We're not getting any lower than this. All of our potential energy has disappeared. It has been converted into kinetic energy. That is to say, mgy0 is equal to 1/2 mv1 squared. We're here solving out for v1. I can cancel out my m's. I don't need to see those things anymore. Move the 2 to the other side. What I should find is that v1 squared is equal to 2gy0. And I'll just leave it as y0 for now. We've got a quantity for that. We can come back to that in a minute here. Plug this quantity in, right? I'm not taking the square root of this thing because I've already got a v1 squared up here. So take this thing, plug it into this expression in my force. What this becomes is now going to be m over r 2gy0. Let's move gravity over to this side, is equal to the normal force. The last thing I can do here is I can slap in what I would be seeing for y0, right? We found last time that it was supposed to be 3/2 r. So what's this going to become? This is now going to be m over capital R, 2 times g times 3/2 r plus mg is equal to f of n. Now I can cancel out those r's. I can cancel out the 2 and the 1/2. What I am left with is 3mg plus mg. That is to say, 4 times mg is equal to my normal force, my apparent weight at the bottom of the ride. Right? And that's your sudden lurch down in your seat when you hit the bottom of the hill like that. So let's say it's a little bit extreme. Let's imagine that for a little bit. Let's say some people have found that this ride is a little bit too intense as it is. We need to lower those forces without changing our height. What's a good way that you could essentially de-intensify this normal force you feel at the bottom of the hill? What do we think? What's a good way to do that? So not slowing down. If we say we still have the same height, we're trying to go as fast as possible. How do you reduce the intensity of this normal force, though? Increase the radius. Exactly. That's exactly it. You increase the radius a little bit, and now, right, if it's a really, really, really short radius, then we've got essentially like a cup shape. And that's going to be your most intense because the centripetal force to keep you in that tiny radius is going to be very, very intense. But if you increase the radius, now that gradual change means you still get the speed, but without the really intense forces seeming to pull you down. On the exam, would you be expected to simplify equations that far? Sometimes. Sometimes, yes. Why did I add mg? Because that was coming from over here. This mg right here, move it to the other side so I can get the normal force by itself. The increasing radius would actually come in right here. Increasing the radius, so we see that there's not really a radius dependence in this portion right here, but if we were to increase the radius, what we're basically saying here is that the centripetal force you would need is going to go down with that. Is that correct? Am I saying this correctly? Actually, in this case, I guess by the dependencies, that's not entirely true, is it? One of the issues that I've neglected here. What is the issue that I've neglected? Why the equations disagree with what I've just said. We've got conceptually the right idea. But why do the equations disagree with what I just said? Where else is the radius showing up that it's screwing up everything we're trying to do right here? How we had found the height in the first place depends on the radius. So this final equation here wouldn't actually change, but the difference is that stipulating on that fact, if we remain the same height, by increasing the radius of this thing, you make it a little bit more level, you decrease the centripetal force in the moment. Right? Now, how we have this thing set up, what we had found the initial height to be, does depend on the radius, so that would modify that. But generally speaking, if you maintained at the same height, if you have the same speed every single time, then the larger the radius, the less intense that normal force is going to be. So let's go ahead and keep moving with it. And I want to take this idea that we just had. Time for the amusement park to get a health and safety inspection. I have actually been going down a rabbit hole recently of a channel that talks about problematic roller coasters, and I keep watching all the old Kings Island ones, and it's a yikes. So let's kind of take that idea that we just saw from before. And if we break this down, this looks like an insane problem at the start, and in fact, this used to be a challenge problem. Like, this would be a challenge problem that a lot of people would work on together. I've done away with some of that stuff, but I want to talk about what goes into this. We have the perfect sledding location. Don't ask me how we got to the top of this thing, because it is perfectly spherical and it is perfectly frictionless. How we got up to the top in the first place is a complete mystery. I assume we were airdropped to it. But we decide to start. We're going to sit at just the very top of the hill, no motion. A particle of dust hits us from the back, and we start sliding down. At what angle phi does the sled fly off the hill? And I want you to think about this. Think about what it means to fly off the hill. Think about what force goes to zero. Think about what's keeping us in the hill, right? Stopping us from detaching. Think about what our speed is going to be as we go down the hill. There's a few different pieces that play into all of this. So I want you to think about those details, group it all together. All of these dependencies, they relate in some way. This is a solvable problem. You don't need anything other than this. I want you to take the next 5 or 6 minutes and work on this one, and then we'll come back together and talk about it. All right, so let's talk about what we got here. So, and I'm going to go ahead and steal this picture, same way as last time. Snippy tool, my good friends. And I know somebody had thrown something up about some alternative way to do that just from hotkeys, but I think that takes a screenshot of the entire screen all at once. Does it not? And we don't necessarily need the whole screen. So let's just start with this. Here's what we got. Got a few different things going on here. I know, for one, that, well, the entire circle is a radius r, right? That's a non-negligible point here, I guess. But when we're looking at this thing, let's think about what goes on with these different pieces. I'm going to draw out a couple different things here, and I want to think about what goes on. So we know, first of all, kind of just on an energy level, we start with a bunch of potential. By the end of it, when we fly off, that's what we're calling the end. That's when some of our potential energy has been converted to kinetic energy. But I can assume here that we're not going to go all the way down to the bottom before we fly off. So I probably still have some potential energy before we fly off the rest of the way. So let me draw a partial circle, and I'm going to use that to help for some of this description. So let's get just like this piece right here. Let's look at that in a minute. And I also want to draw out a free body diagram of what's going on. So let me get another one of these things, copy this in the exact same way, Let's have one of these for just a description, one of these for a free body diagram. So as we're talking about this thing, when we are at some spot along, let's talk about like right here, for example. Here's where our sled is. Think about, excuse me, think about the forces that we've got. We know that there's going to be a normal force, and that is directly out from the surface, right? It is radially away from the surface. So there's our normal force. Gravity going to be pulling down like this. Now, to stay in the circle, to not fly off, I've got two different things going on, right? The big one, though, is that I'm no longer able to maintain the centripetal force necessary to keep the sled in the circle. So we're in the situation again, where the normal force goes to zero. What is there from gravity is not able to provide, or is just barely able to provide, our centripetal force. We need to think about what goes on with some of these pieces, though. See, not all of gravity is actually going in the centripetal direction, or the radial direction, I should be saying here, right? Some of it is going just straight down, tangential, right? And that's kind of what we expect, because we're not moving in a uniform circle anymore. We are speeding up as we go through. So I know a couple details here. I know that if this is supposedly phi, then so too should this angle be phi. Right? I also know that if I'm to stay inside of a circle, I need a centripetal force, mv squared divided by r. I know only part of gravity is actually helping with that, and what part of gravity is actually helping with that is the cosine. Right at the very top, when phi is equal to 0, gravity points directly down. It is all going in the radial direction. As I curve more and more and more, less and less and less of gravity actually points in that radial direction. So that is to say, this comes from mg cosine of phi. Now, typically, we would say, okay, well, that's great, but normal force is pointing away from this, right? Based on our picture, that's what we see. This is what's going on in the radial direction. I shouldn't even say centripetal force. I should say the radial direction. Radial direction being like this. Tangential direction being like this. Some of gravity points in the tangential direction, and I really don't care about that part. I'm not interested. We know when we launch, this has gone to 0. So I've really got mv squared over r is equal to mg cosine of phi. Now, this is half of my picture. Or rather, half of my solution. I've already got the full picture, right? So here's what I've got going on with my forces. This is basically setting a condition that we say we know we're at this angle and this velocity when we fly off. So that's 2 points, but 2 unknowns. We can't solve this thing out quite yet, right? And let me highlight those like I normally like to do. We're looking for phi. To find it, we need to first find what this velocity should be. So the other place that this is going to show up is, of course, going to be in energy. We have already used our forces, so let's look at energy instead. In terms of energy, let's go ahead and say forces. Over here, energy. We started exclusively with gravitational potential energy at mg capital R. That was our initial height. What we end with, well, we should have some kinetic energy, but we also will still have some final height. Not all of it has gone to kinetic energy yet. Some of it is still potential. All right, well, how much? Let's look at this thing again. Let's say here's our sled, as we've got it, of course, a very nice aerodynamic looking sled. How do I actually find that height? Well, here's what I can do. Let me split this thing up like this. Straight down, straight over. Let's make these dotted lines just so we're not confusing ourselves here. Dot, 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 something like that. Dot, 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 something like that. Because it's not anything physically there. We're just trying to set, essentially, here's my vertical and horizontal lines. It always, always, always comes back to triangles. Always. When has it not come back to triangles? We've got a triangle that looks something like this. I know that this is a right angle. I know that the hypotenuse of this triangle is capital R. I know that this angle of my triangle is phi. Right? That is to say, if I am trying to figure out what height am I still at, what is this height right here, y final, it's a cosine. SOHCAHTOA tells us that the adjacent side length, y of f, is equal to r cosine of phi. Plug it in. This now becomes mg capital R is equal to 1/2 mv squared plus mgr cosine of phi. Okay, now I run into a little bit of an issue. I said I needed to find v first before I could find phi. But my expression for v here also depends on phi. So it's not going to be quite as clean of a solution as we had hoped it would be. V is right there, phi is right here, but it is still solvable because if we notice, we have two unknowns, but two independent equations. So it's now solvable, we just need to figure out the rest of the algebra to make this happen. The physics is done. What's the best way to do that? Well, I would probably like to isolate v first. That's probably the best way to go about this. So let me cancel out these m's. We don't need all those things floating around. Let me separate out v all by itself. So what this is going to become is v squared is equal to g capital R plus, whoops, not plus, minus 2g capital R cosine of phi. And I can even simplify this a little bit more if I would like. I notice that I've got a v squared over here, so I'm not going to bother with the square root. I'm just going to plug in the v squared. But I can maybe make this a little bit easier for me to work with. V squared would be equal to 2g capital R, 1 minus cosine of phi. This might just be a little bit easier to deal with. So we've got this in place. 1 minus cosine of phi, by the way, is not equal to sine of phi. Don't get caught in that rabbit hole. It's a little bit different. Here's what I can do instead, though. Let me take this expression, and let me now plug this thing in. Take this, take it all the way back over here, right? A long journey. All the way over to here. While I'm here, let me say, okay, let me cancel out the m's just in the same way. Don't need all those things. V squared over r. So 2g capital R, the r gets canceled out. I'm left with 2g, 1 minus cosine of phi, is equal to g cosine of phi. We don't need those g's. Cancel those out. So we know that even if we had found this perfect sledding hill on Mars, it would still work in the exact same way. But now I need to find some sort of way to simplify this thing. Probably the best way that I can do this is that this is going to become 2 minus 2 cosine of phi is equal to cosine of phi. That is 2 is equal to 3 cosine of phi. That is 2/3 is equal to cosine of phi. Take the inverse cosine. Taking the inverse cosine of this thing. Should net us a final angle of 48.19 degrees. How do we feel? Do we love triangles yet? Are we having a great time with it? What am I saying? Of course we are, right? I can zoom out a little bit on this so we can see all those lovely details. Yeah, it's kind of nice. It looks like a really complicated problem, but it comes down to two kind of short columns, really. But I think I've been talking with a few different people about this. A conceptual understanding of what's going on is critical. Arguably a lot more critical than algebra, because in algebra, you can kind of flop around with algebra a little bit, right? If you need to write down every single step, if you need to modify it in a bunch of different ways, that's one thing, right? But understanding what equations you put down in the first place, that comes a lot more from a conceptual understanding of what's going on. That's a really critical piece. And when I'm talking about some of these things, I know that I'm not writing these down as much, but if you look at a lot of my solutions, I put a lot of little snippets in there. And sometimes, you know, I'm even cutting some of the corners on that one, but like especially my whiteboard solutions, I try to be very, very dense with what I'm writing down in my whiteboard solutions. I try to write down every single step along the way, descriptions of every single piece here. If you haven't been looking at these things, like here's kind of roughly what they look like. Right? I've got like sentences describing what goes on here. I've got these little spots in blue that are my personal thoughts on as I'm going through these different steps. Kind of in the pencil writing, I've got the big main steps of the problem. I try to do this to make sure that I've got a thorough understanding of what's going on with the problem. It's not just necessarily explaining it for you guys. I mean, that's why I'm writing down the solutions in the first place. But a lot of this is my solving process. My solving process is to start from, I'll start in some different places sometimes. I'm not always consistent with that. But a big part of it is that I'm trying to describe what goes on in every single step. What goes on with the problem as a whole? What's going on specifically right here? What about right here? Why is it like this? Why is it not like this? I need answers to all of those questions. If I don't have answers to those questions, that's a spot either that I need to look at that might help me solve the problem or highlight a misunderstanding I might have. If I don't have the answer to why it's like this and why it's not like this, that's a fantastic time, you know, so this is from your perspective now. If you can't come up with an answer for why it's not like this, but it is like this, even if like you're like, well, I know this is right, but I don't know why, I can't explain it, that's the perfect question for me. Right? Send it to me in an email. I'm more than happy to chat about a lot of these things, to clarify a lot of details, all of that good stuff. But that's my problem-solving process for all of these things. I like to write a lot of descriptions, and instead of writing them down on this one, I'm just saying them out loud instead. So, in that case, I know we're doing kind of a weird hodgepodge of things. We've got some things from Chapter 10 here. Now we're diving into some things from Chapter 9 again. Again, the material's all a little bit weird. But, talking about springs. Most springs, the general assumption for springs is that they are linear. There's a fancy equation called Hooke's law that tells us what the force looks like coming from one of these linear springs. So generally speaking, as long as you're not bunching them up, right? You know that when you take a pen spring or something else like that, stuff gets a little bit funky. Of course, I can pull one of these things apart, right? I am talking when a tiny little spring, if you have a pen nearby, you can take one of these things, right? When you push down and push back and forth and everything else like that, that is in linear motion. If you really squeeze it tight so that pieces are bunching up on each other, Hooke's law kind of falls apart. But Hooke's law does a very fantastic job of talking about the basic motion of springs, or the basic characteristics, I should say, of springs. That is to say that if I stretch a spring, if I stretch a spring, it wants to go back to its original shape. If I compress a spring, it wants to go back to its original shape. That's why, when we're looking at this equation, the spring force equation is negative kx, because if we go in the positive direction, it wants to pull back to where it was. If we compress it, if we push it into the negative x direction, it wants to go back where it was. But the force of the spring depends on how compressed or stretched it actually is, right? As you compress or stretch it more and more and more, the force increases, and it does so in this very linear fashion. So, springs are another example of a conservative force. They're wonderful. They're great because we can always expect them to be pushing by the same amount when they're in these different positions. We can also call these things linear restoring forces, which has nothing to do with necessarily what goes on with it, whether they're conservative or not. It's more dependent on the fact that wherever it is now, it wants to go back to that, right? The negative sign says it's a restoring force. The fact that it's a linear force means it's a linear restoring force. It wants to go back to its original unstretched state. So, We also have the spring constant, by the way. That is a given value. It depends on the spring, right? Different springs will have different spring values, and that's just talking about the stiffness of the spring. Is it really flimsy? Is it really solid? That all is included in the spring constant. So taking that equation, knowing that idea, and I'll write this thing down right here, F is equal to negative K spring force, or spring constant, times X. The restoring force of 3 springs is measured. I don't know whichever one that is. I picked is at the time. As they are stretched. Which spring has the largest spring constant? What do we think? A, B, or C? They're not all the same. If I think about this just like an equation, if I have a function that depends on x, and that dependency is some constant times x, that constant is the slope of my function. The greatest constant comes with the greatest slope. That is to say, I only need to compress it a little bit to get a lot of force. Whereas something like C, I have to compress it a lot to get that same amount of force. A is the most stiff spring. A has the highest spring constant. Or largest, I should say. Does that make sense? Okay. So, if we take this idea, and we say, okay, well, it's got a force associated with it, and then right in there, the force has a distance right attached inside of it. There's a distance dependency on that, which means it's going to be a little bit more complicated. But if we take this idea, and we think about what is the work done by a spring? What is the potential energy associated with a spring? We would have to take that integral. And because it's a non-constant force, we actually do have to take the integral side of things, but it's not a complicated one because springs, we're not going to consider springs that go in like 5 different directions or something, right? We're just talking about a regular linear spring. My force is negative kx. My dx is, well, in the x direction. So I'm just integrating negative kx. That is 1/2 kx squared. And what I find is that any time I'm talking about this sort of compression, wherever I am to wherever I go next, that has some spring energy associated with it, 1/2 kx squared. Delta x squared, specifically. Now, we like to take this nice clean solution. X is equal to 0, our initial, but it works out just fine. We just need to look at essentially the difference between 2 different states. So this is our expression, though, and this gets slapped right in with our other energies, right? So now we have kinetic energy, we have gravitational energy, we also have spring energy. All 3 of those. They might not all show up in the same problem. We might only have potential to spring. We might have some combination of all 3 into some other combination of all 3. That's totally fine. It's just those energies might be present. But you can treat it as if it is another potential energy. We can talk about this thing in terms of, so we have a spring force. A spring force, it has a distance already kind of tied in with it, but a spring force can be integrated to become a spring work. That is, if I were to compress or to stretch a spring, there is some work associated with doing so. The spring is doing some work. How much work? We can go through that integral and we find that it is negative 1/2 kx squared. Remember our old definition here that says a potential energy is essentially just the reverse of the work, right? When gravity does a negative work on an object to lift it up, that's basically saying this energy is stored for some time later. It's willing to give that back. It just took it away for now. Same thing with springs. When I compress a spring, the spring has eaten up that energy. It has contained that energy in a potential spring energy. If I release it, then it gives all that mechanical energy back. But what we're doing here to make this a little bit easier, we're saying that it's 1/2 kx squared because we assume that we're starting from an uncompressed state or an unstretched state. We are completely spring in equilibrium, right? X is equal to 0. There is no force done by the spring. It's just sitting there, right? If we were to compress it or if we were to stretch it, either way, then we have some change of its energy. But that change of energy might just show up. You can at any point say the energy contained in the spring is 1/2 kx squared. It falls right into our big energy conservation equation like this. Our big energy conservation equation is just basically saying we might have kinetic, we might have gravitational, we might have spring energy. All three of those might show up. They might be in the initial side. They might be in the final side. But I know if mechanical energy is conserved, then both sides have to be equal. Okay, I do want to try this one out here because we do have a couple other problems here to talk about. Let's dive into these and let's see if it works a little bit better. Maybe a working example will help this. So, aircraft carriers, right? Very neat, very short runways. They're a little bit difficult to work with because realistically, as big as aircraft carriers are, they are not a full runway, right? They're only really part of a runway. So when you're having to launch a bunch of planes off of these things, they're having a little bit of difficulty. And even more difficulty than that, launching is one thing, landing is another. There is not enough room on an aircraft carrier to actually slow it down to a stop to land on like a normal runway. So what they have is a hook on the back of all of these planes, right? And this is almost kind of a crazy simple solution to probably some of the most expensive pieces of equipment in the world. There's a hook on the back of these planes. When they are landing, they lean down just a little bit. They angle in such a way that the hook catches onto some very large rope, and that very large rope pulls on the back of the plane and slows it down before it falls off the other end, right? And this is why you might see like pilots in training on aircraft carriers might have to make a few passes before they actually, correctly land with this thing, catch that thing and actually slow down enough to land. So, more or less, we know it's a rope, it's got a big steam piston system and everything else, but what we can generally model it as is a big old spring. Let's say that it's a spring with a spring constant of 60,000 newtons per meter. So K is equal to 60,000. If the spring stretches 30 meters to stop the fighter, and the fighter's mass is 15,000 kilograms, what was the plane's landing speed? So no difference in gravitational potential. We assume that we're already on the runway, we're not changing height at all. But we start with a bunch of kinetic, and we end with a bunch of spring energy. I want you to take the next 3 or 4 minutes, work on this one, and then we'll talk about it together. Okay, so let's give this a shot. One of the fun things with a lot of springs is that you can do a lot of different things with them, right? They're often used as dampeners in different ways, but realistically, you can make a pendulum out of a spring, for example. If you have like a frictionless track or something else like that, something will oscillate back and forth on a spring. It works out just like a lot of other types of potential energy, just like gravity. A pendulum just as essentially is back and forth between potential and kinetic. So too is a spring pendulum, back and forth between potential and kinetic. So, if we were to draw out a picture of what's going on here, let me set this thing up like this, like this. Here's like my track that I'm going over, right? Can't you tell? This is an aircraft carrier. So we've got something like this. And then let's try to draw the plane. Oh, geez. Oh, this is going to be a disaster. What do planes look like? So we've got something like this. That's supposed to be a tail to the plane, right? And then there's like wings on planes, normally, I think. Looks like that, and then like a nose cone, something like that. Oh yeah, that's an expensive looking jet. And it's got like wheels. Beautiful. Yeah, that's it. Okay. Now there's a spring attached to this thing. And that's how we draw springs. Now, in our second picture, so this is our initial. In our final picture, we have now stretched by quite a bit. Our same plane from before. I'm not going to try and draw a masterpiece twice in a row here. Let's go ahead and steal this thing. Now, it's farther down the track, like right here. And our spring has done something. Selection mask, please. No. Our spring now looks something like this, right? Now it's a very stretched out spring. So there was some delta x associated with that. Some change in x. So it started completely uncompressed. In our initial picture, before anything was happening, we knew that the plane had a velocity to it. That is, all of our energy was in kinetic. E initial must be 1/2 mv squared. At the very end, the plane has stopped. All of that energy has gone into spring energy. Our spring has stretched. In doing so, it has absorbed all of that energy, it's kept it up, and we have slowed the plane down to a stop. E final, now the spring is containing all of that energy. There is no kinetic energy left. And the how question, in which part here? How is it kinetic energy and not potential energy? Because the plane is moving when we start, right? There's nowhere for the potential energy to be. It's already on the runway. There's no gravitational potential energy because there's no change of height, but we are moving. This is not launching off. This is slowing down, slowing to a stop. We have just come in from some sort of test flight or something else. We have a high speed as we land on the runway. So we initially are just kinetic energy. Then we catch the spring. All of our kinetic energy gets fed into the spring. So we end with exclusively spring potential energy. That is to say, 1/2 mv squared must equal 1/2 kx squared. I can get rid of those 1/2s. We don't need both of those. We are looking for our velocity, but we know, let's go ahead, I have neglected our given variables. We are given, the mass is something like 15,000 kilograms. We know that the spring is stretched to, I think we said 30 meters for that. 30 meters. We know the spring constant K is equal to 60,000 newtons per meter. That is, every meter it gets stretched, it provides 60,000 newtons of force. With all of those variables, the only thing we don't have is V. We are freely able to solve this thing out. We should find at the end of the day that V is equal to the square root K delta x squared divided by the mass of the plane. Plug in all the variables that we have, and what we find is the plane came in at 60 meters per second. It is potential energy at the end. At the very end of this, it is potential energy. It's just spring potential energy. It's not gravitational potential energy. Right? When we were looking at this conservation equation right here, there are two different terms for potential energy now. We either might have gravitational potential energy or spring potential energy. But both of them are considered potential energies because they're coming from conservative forces. They're places that we can store energy for later. Now, how we do that within the aircraft carrier is that this thing locks in place essentially, and then over time, it gets released back to where it started, right? They don't just snap this thing back because that would be, all of the energy that we put into it in the first place would suddenly snap back for a second. Trust me, simple math is a brutal foe, one that I still fight with every day. In which case will the energies not be equal? When friction starts getting involved, but even then, we can get around that sometimes. See, talking about these dissipative forces, diving into stuff like that, we can remember here that work, anytime we're talking about work, it's anytime I've got a force acting over some distance. So if we even wanted to talk about this, let's imagine friction got involved. If friction had been involved here, if we were also activating, say, the brakes of the plane, right? Because most planes do come with brakes on their tires and everything else. So let's say it's not just the spring, but it's also the brakes. If it was also the brakes, what that would be saying is that there is some energy eaten up by the spring, and at the same time, some of our energy is going into, not a 1/2, what am I thinking here? The work done by friction. What is the work done by friction? Well, it's our friction force. So kinetic friction times the delta x. I know oftentimes in the book it's related in such a way that the change in mechanical energy is equal to friction, or specifically negative friction. I'm not a big fan of that. I think it's a little bit more clear to say, hey, friction was here. Friction stole some of that energy. Right? Not all of our energy just went into the spring. It went into other places. It's just we can't get it back. It's there now, released into heat, released into sound, whatever it's doing over there, but it is a place where the energy went. So I like to think of it as always the initial energy is equal to the final. It's just we might have some extra terms here where energy is going. So depending on what style you like, it might be that our initial and final don't equal each other when there's friction, or sometimes you might be able to include it to say it's always equal. It's just friction shows up in one of those terms. Okay, let's look at this very last one, though, because I do want to talk about this. So let's say your sledding experience, you're like, that's 1 in a million. A frictionless, perfectly spherical hill. Where else am I going to get a thrill like that? Probably nowhere, but you're going to try anyways. You're going to go bungee jumping. You're on a bridge that is 100 meters above the roiling river below. You have a 30-meter long bungee cord. What that means is that the rope before stretching is 30 meters long. A bungee cord is, for all intents and purposes, a long spring with a spring constant of 40 newtons per meter. Let's assume that your mass is 80 kilograms. How far above the water are you when the cord reaches its maximum elongation? Think about all of the different forms of energy that you need. And I'll give you a hint. You don't need kinetic energy here. You can ignore kinetic energy. Not that it isn't there. It's just between our initial and our final. In both of those steps, kinetic energy is not a factor. So, I want you to spend the next 5 minutes working on this one, and then we'll come back and look at it together, and that'll be the last thing that we've got for the day. All right, so let's start to take a look at this one. One of the big details here that we need to worry about is how all of these forms of energy are going to be changing between each other. So let's think about it like this. We're starting on top of the bridge. We have our roiling waters below. Let's go ahead and draw it. Roiling waters, I imagine they look something like this. Right? That's what it means to be roiling, I think. So we have some sort of height between these two. Let's just call it h for now, right? We know that h is equal to 100 meters. Given a few different details here. H is equal to 100. That's one detail that we've got. We also have some other details. So initially, we're standing up here at the top, excited for this thrill. Then we jump. And for the first 30 meters of this, we have to think to ourselves, hey, I don't feel anything pulling from the bungee rope. Is this it? The bungee rope has so far not actually stretched. So here we are, again, excited, but perhaps now terrified. As we fall, that first 30 meters, call this distance x naught. X naught is the initial length of the bungee rope. Right? Up until that point, it is not going to pull on us. We fall the first 30 meters before the bungee rope actually starts to pull. By the end of it, what we should see is some mostly straight line down, kind of like this, all the way down to the bottom, where we are now, I don't know, stretched or something else a little bit more than we were before, and some final height to us at this point. So that's what we've got. We're looking to find the final height, YF in this case. So what I can do as well, though, is I can say, okay, well, there was x naught like that. Let's call this distance now x of f. I've got a few different relating details on all of these things. I know a few things like the mass is 80 kilograms. I know things like the... what am I thinking here? I don't know anything about x of f, but I do know that the spring constant is 40 newtons per meter, correct? 40 newtons per meter. So we've got as much information as we need to actually solve this thing out now. But let's think about this. Where is all of our energy when we start? What form is it in? And don't just say potential, because now we have a few of those. It is all gravitational potential energy. That is exactly correct. And how much do we have? Well, we have mgh. What about all of our final energy? What does that look like now? It's not all spring energy. Some of it is. A lot of it is. But it's not all spring energy. Because if we smack into the water, usually that's not what they try to do during bungee jumping. Usually that's not great. We know that it's not kinetic anymore because this is where we have bottomed out. We have stopped moving, right? That's the whole point of the bungee jump, is that you jump and then it catches you and it brings you back up. So we are in the catch and get ready to start bringing back up stage of this entire thing. We are no longer moving. There is no kinetic energy associated with this, but we are still some height above the water. So there is still some potential energy in gravity, but there's also the rest of it is now in our spring energy. So I'm going to say this is 1/2 k delta x squared, where delta x is this difference between x of f and x naught. It's some number. So what we need to do is we'll figure out what we have and what we don't here. So I run into a little bit of an issue. I want to know how high I am from the water, y of f. We already know h, we already know m, we know k, and g has been 9.8 for as long as we've been in the course, so that's not it. But I don't necessarily know what delta x is. I do know part of delta x. I know the initial length of this thing in the first place, but I run into a little bit of an issue of how do I tie that in with anything else I'm doing here. An easier way to go about this is to say, okay, well, with all of that in mind, I know that delta x actually kind of depends on y of f, right? They share this relationship between each other because the shorter x of f is, the larger y of f is. So there must be some relationship between the two. I'm not just going to find a number for delta x on its own. I need to figure out what is an expression for delta x. And I think the easiest way to do that is to say, well, how much we stretched this delta x is perhaps better written in a big long equation like this. We could also say that delta x plus y of f is equal to h. And why would I do something like this? Because now what I could do is I could plug in all of these things. F of f minus x naught plus y of f is equal to h. That's not the better way to do this. Let's just leave that as delta x. Just kidding. Let's just leave that as... what have I done here? I have made this, I think, a little bit more difficult than it needs to be. The best way to write this out is probably going to be something... Let's see here. What have I done? Let's replace x of f with some other details. That's what I'm thinking here. So we know that this expression delta x is sitting right here, but our actual height that we fall is going to be this initial height minus y of f. So we can plug in this expression. We can say, I'm messing this up somewhere. Hang on, give me a second. I've worded myself into a strange place, and I think I've messed up something a little bit in how I'm describing this and how I'm writing this. Give me just 1 second here to read, so I don't put my foot in my mouth and say something dumb here. It is better written as x of f, I think is what I should be saying here. Yeah, why would it be delta x instead of x of f? Because what I'm trying to say here with the delta x is that it's the difference. We fall the initial x naught, and this is where it's uncompressed. That's our initial fall before we have actually done anything, right? Because it starts 30 meters long. For the first 30 meters of our fall, there is no energy going into the spring. It's not until we hit 30 meters down, that's when the bungee rope starts to stretch. That is the distance that we're after here. So let me think about this a little bit here. Let me think of a good way to do this one before I screw up anything. Why? None of my things are erasing. That's fine. I have just thought about this and written this out in a little bit of a strange way. It's not that x of f is our full spring distance. It's as we have this thing, it is this difference between x naught and x of f. If x of f is the full thing, I've written it incorrectly down here is what I think I'm... What layer am I supposed to be on? Ugh. Give me a second here. Apologies. And if anybody needs to go, this lecture will be up in just a little bit if you'd like to look at it then. I have just bonked this just a little bit here. Give me a second here. Delta x plus y of f is not equal to this thing. Why is this not working? Is it just doing its normal thing here? Yeah, it is. Okay, sorry about that. Drawpad was messing up, but I didn't realize. What I should be saying here, I screwed up. I figured out what I screwed up here. X of f plus y of f is equal to our initial height. So we know that delta x is equal to x of f minus x naught, but I really don't care what x of f is, right? That's not a factor in any of this. So let me take this equation. Let me say x of f is equal to h minus y of f. Let's take it up to my delta x. delta x comes down, and then I say delta x should be equal to h minus y of f minus x naught. Now, this looks a little bit spooky at first, and I'm doing this symbolically in a little bit of a strange way, but h and x naught are both variables that we have. I can plug those in and combine those into a number. So I'm about to plug this thing in right here, but what I'm going to find is probably the easier way to do this. We do need to do this with a quadratic formula, and let's see that real fast. But I could write out that delta x is actually just going to be our 100 minus 30, so this is 70 minus y of f. 70 minus y of f, we plug it into our equation up here. If we plug in all of our variables, which is probably the easier thing to do at this point, plug in all of our variables, find some numbers. We're trying to get this thing into quadratic form now. If we do that, we plug in all of our numbers, what we should find is something like 1/2 of 40 minus, 40 times 70 minus y of f squared, my term right here, plus 80 times g times y of f, my term right here. So let me erase this. Let me do it like this. Here's my three terms all coming together. 1, 2, 3. Minus MGH is just 78,400. My three terms as I have them. I go to my, I need to simplify this first term right here just a little bit more because it's going to split up. So let's say still 0 is equal to 20yf squared minus 2016 y of f plus 19,600. We go to our handy dandy quadratic calculator. We slap all of that stuff in. We find two different answers. And let's think about what these mean, because both of these are actually going to be positive. Our two different answers are going to be 89.9 and 10.9. Why does 89.9 not make any sense? It's not that, so we're finding y of f here. So that's not to the point where we have gone down. That's saying that this would be true if we were right here. The answer doesn't make any sense. We know we fall the first 30 before we actually feel any force from the spring in the first place, right? Because what's going on here is that this spring force, as it is, doesn't care which way we're going. It doesn't care if we're compressing or if we're stretching. So we're looking specifically at the case where I have stretched out the spring. This solution down here, 89.9, is assuming what happens if, the same condition, all kinetic energy is 0, but you've compressed the spring instead. It doesn't work like that because it's a bungee rope, it doesn't get compressed. This answer doesn't make any sense because we know we fall the first 30 before the bungee rope is even a factor. 10.9 meters is our answer. Apologies for the little hiccup in the middle there. I wrote down something wrong and then didn't realize it at first and confused myself and turned myself all around because what I have here on the side for my solution certainly did not match what I had over here, and I couldn't exactly figure out why. So apologies for that. It made me drag a couple minutes over here. So, yeah. But if we have questions over this problem, over anything else on the lecture or anything else like that, would it be easier to say that before you jump y is equal to 0 and then subtract what you get from 100? I don't think so. The only reason I think that shows up, it shows up in delta x anyways. You don't get a much easier problem if you subtract from it later on because that's basically just flipping that equation the other way around. Now it would be some negative 30 minus y of f, or something like that. Yeah, I don't think it actually simplifies things by much. You should still be able to do that just fine, but I don't think it makes it much easier than what we've already got here. And then how do we get to the 19,000? I've got my 78,400 from right here, but so that's part of it. But that 78,000 is going to also combine with, I've got this thing, right? I've got a polynomial that needs to be distributed. I need to FOIL that thing out. So part of it is going to go, and this is the reason why we have these things split into two steps here. Part of it is going to be just a yf squared, right? And that plays down into that one. Part of this is going to be the yf times the 70, and that combines with these two into that. And then finally, I have just the 70 squared portion, which combines with this. Yes. You could. So the question, and I'm going to repeat this just because I'll probably include this in the recorded version here. The question surrounding, can we just start from the 70 and then just go from there? Yes, kind of, but it's more work actually, because in that case you have fallen the first 30 meters, and while you only have 70 meters of potential energy left to go, that first 30 meters has given you some kinetic energy. So now our starting point has potential and kinetic energy, rather than our starting point just having potential. Absolutely. Yeah, that's just a general note on these things. If ever I repeat the questions or anything else, none of your voices ever get recorded in these things. It doesn't go onto Twitch or anything else like that. I have it strictly set so that the only sounds going into the recording and onto the stream are from my side. But because of that and everything else, sometimes I will repeat your questions or read them aloud or anything else like that, just so there's a little bit of context for anyone who doesn't get to see that question, whatever chat it's in or anything else like that.